Hello! Well, here I am back in front of the camera. I took a couple of weeks off to do some other work. My last video was a rather long video, so I decided to take some time and do some updates on the Vocademy website. And in looking for what needed work, I saw that my page on laser has a disclaimer at the top saying, "This is how everyone says it works, but that's not quite right. I'm going to make a better explanation later." I said, well, that'll be something I can do in a day or so. And 2 weeks later, I'm still not quite finished. It turned out that that was quite a rabbit hole to go down. So let me explain what's going on there and give you a little precursor to what we're going to talk about with laser. And I'm not quite ready to make a video. The page for the website is not quite ready, but I need to update you guys on what's going on. And of course, a big thank you to all of you who are supporting me through all of this. I can't make as many videos as I'd like because I am the producer, the writer, the editor, the presenter. I do all these jobs myself, plus I maintain the website. There's an awful lot to do, and I can only do so much. And I, again, want to thank all of you who are sticking with me and continuing to support this channel, even though I may not be able to make as many videos as I'd like. Maybe the production quality isn't what it might be if I had a production crew. And because I can't interact with you as much as I'd like, because I really have a lot on my plate and I do as much as I can. I will interact some, but there's just only so much that I can do. So a big thank you for sticking with me and continuing to support this channel and making this possible. And most of you are doing this through Patreon, and to help me do this, you can go to patreon.com/Vocademy and make a monthly pledge. And you can make one-time donations at paypal.me/voced, V-O-C-E-D. Those are the best places to support me. There are other ways to do one-time donations, but they take a lot more money than PayPal does. So I really recommend you go through PayPal if you want to throw me a couple of bucks. And again, I can't interact as much as I'd like. I read as many comments as I have time for, and I respond to as many as I have time for. And if you're asking me for help on projects, that's probably not going to happen. It depends on how complicated it is. But if you do have a comment to make, especially if you're asking questions, I highly recommend that you ask those questions in the comments for a relevant video, because then if I don't have time to respond to it, somebody else often will, and you'll get some kind of an answer, because I just can't guarantee I'll have time to respond. But again, a big thank you for supporting me, even though I cannot respond as much as you may wish I would. So let's get on to what happened, what I'm doing about laser, and how much I'm learning, which is way too much. Here's how it started. Back in the day, which has been quite some time now, when I was actually teaching in a classroom, I was teaching a fiber optics class, and one of the videos we showed talked about Fresnel reflections. And one of the students asked, what is a Fresnel reflection? And instead of giving the quick hand wave answer of, well, it's the kind of reflection you get off of glass or water, or when you have light go from one medium to another, and just leaving it at that, I decided to try to give a more technical explanation. And while I was doing that, it occurred to me that the typical explanation about how laser works is incompatible with the explanation about how Fresnel reflections work, which I think is a lot closer to reality. So first of all, let me explain Fresnel reflections real quickly. And if you've seen some of my other videos about the nature of light, especially my last one I just made where I talked a lot about it, you'll know that I am learning that light is a quantum object, and it's all about probabilities and expanding waves, and it's kind of fascinating, and I'm hoping I'm explaining it right, but I'm giving the best explanation I can with my knowledge of the subject. So here is my understanding of Fresnel reflections. Let's say we have a material, let's say we have some glass here, and so out here is air, here is glass, and I'm just going to draw some dots which represent a bunch of molecules of glass. I'm making way too many dots here, but we'll work with it. And now here comes a wave front of light. So here it is, there's a wave front, which is many photons working together to produce this wave, which is actually a wave of probability more than anything physical, but we won't worry about that too much at the moment. And this wave is traveling toward this glass and is traveling at the speed of light through air. And when it hits the glass, we know that it slows down. Well, what's going to happen is that when it hits the glass, this light is going to react with molecules of glass, which are going to be silicon and oxygen and some other materials, but we're not going to worry too much about the exact composition. And when it reacts, what's going to happen is that electrons in these atoms are going to absorb those photons. So most of these photons will be absorbed. A few might get away, but that's neither here nor there at this point. The photons will be absorbed and they're gone. So when a photon is absorbed, all of its energy is gone. So this wave completely disappears and all of its energy goes into raising electrons in these atoms to higher energy states. Well, the molecules of glass don't have any energy states, assuming this is visible light and this is typical glass. There are no energy states where these electrons can loiter around and hold on to that energy. So I saw a demonstration of this. I think it was from, I think the channel is called 60 Symbols. You may have seen it. And the physicist was explaining it's sort of like bouncing balls at a shelf. You throw the ball at the shelf, and if it has enough energy to bounce off of the ground and onto the shelf, it might get stuck there. It might bounce back off, but there's a probability it'll get stuck there for a while, and then maybe it'll fall down later. But if it doesn't have enough oomph, enough momentum to bounce up to that shelf, it's not going to make it and it's going to go right back to the floor. And of course, in classical physics, it's going to lose energy in bouncing, but in quantum physics, that doesn't happen. But the idea is that these electrons absorb energy. There's no energy state low enough for them to loiter at. And so they're going to fall back down. And when they do, they immediately lose that energy that they absorbed from that photon. And so what does an electron do when it loses energy? It emits a photon. And it's going to emit mostly the same exact wavelength or frequency of the light that hit it. And so we get new photons. And I'm going to show them as expanding circles. I don't want to draw too many of them. So these photons are going to be expanding waves, like dropping a rock in a pond, you get expanding waves. These are going to be three-dimensional waves. And as they expand, hopefully I can draw this. I'm going to draw them after they've expanded a while, and they're going to start overlapping. Wait for that Pilatus or whatever it is to go over. And I don't think you can see it now, but I will draw them a little bigger. And maybe we can see it out here. I'm going to try to make an animation to make this a little more clear. Yeah, it's not too good, but you can see they're kind of lining up along this front and along that front. So if I kind of draw it out here, I'll draw just a few circles. I'll make them overlap a lot. And I think, yeah, that's giving us an idea of what we'll get. And so notice that there's a wave front here and a wave front there. And these are waves of probability. So the probability of these photons interacting are being concentrated along these two fronts and not very much along the ends. And so we end up with a wave front going into the glass and a wave front going away from the glass. So that's why when light hits glass, some of it goes through and some reflects off. And if this comes in at an angle, I'm going to have to redraw this. Otherwise, it'll be totally incomprehensible. So here's our glass again. If this wave comes in at an angle, it's going to energize an electron here and here and here in succession. So it's going to get that one, and then that one, and then that one, and then that one. And so this one's going to start expanding, and then this one will. But by the time this one gets that big, this one is that big. And by the time this one reacts and it's that big, this one's going to be that big, and that one's going to be that big. And notice that the angle, if I kind of draw it here, it should be a, well, let's go ahead and draw that out there. If we draw a line perpendicular to the glass, the wave coming in is going to be the same angle as the wave going out. And so that's how Fresnel reflections work. And what we have are these waves of probability. And notice that the photons are expanding rings of energy, not, well, we're looking at them as waves, not as particles, because as I explained in other videos, the particle part of the wave-particle duality of light is probably an illusion because of the way we look at it. And we'll see a little more of that in a moment. So that's Fresnel reflections. Now let's go and talk about the typical explanation about how a laser works. Another thing about the way electrons act, and I'm going to explain a lot more about this in a subsequent video, but electrons and photons have a very intimate relationship. And if an electron loses energy, it emits a photon. And that photon is going to have the same energy that the electron lost. And there's going to be a wavelength to that photon that's tightly correlates with that energy loss. I don't have any numbers off the top of my head, but I'm not going to worry about that now. We just know there's a particular amount of energy, and that amount of energy will have a particular wavelength or frequency depending on how you want to look at it. Also, if a photon encounters an electron and they do interact, there's actually a very tiny chance that they will, but if it encounters an electron and they do interact, that interaction is going to be that the electron takes all the energy from that photon and that photon is now gone. So we know that electrons can gain energy and move to higher energy levels, or they can lose energy and give off photons. They can gain energy from photons or from electric fields or from heat, but a photon can also give its energy to an electron, in which case the electron takes all the energy from that photon with some very specific exceptions, but we're not going to worry about that at this point. So we have a proton, and here's the electron orbitals or shells or energy levels, the n equals 1, n equals 2, n equals 3. And we'll say that we put some energy into this hydrogen atom and kick up its electron up into the n equals 3 level. Now remember, if this falls spontaneously from the n equals 3 to the n equals 2, remember it's going to give off a photon of hydrogen alpha light at a 656 some odd nanometers wavelength. Now let's say there's another photon coming in, and it happens to hit this photon and they interact. It's very likely that it's going to cause this photon to fall right then. It's going to stimulate it to fall. And so now we have two photons going away, and the two photons will be identical. They'll both be the same wavelength, the same phase, which means that they are lockstep in with each other. They're going to have the same polarity, so that the positive end of the wave is going to be the same orientation. So if the positive and negative orientation is horizontal, they'll both be horizontal, or whatever angle that might be. And they also are going in the same direction. Now, this explanation, if you understand the latest theories about quantum physics, we've got a problem with it, because this whole idea of photons being a particle is not as simple as it may be presented. Because when this photon hits this electron and stimulates it to emit another photon, remember what that photon is going to look like? It's an expanding circle. So I can buy that, okay, they're the same frequency, because what frequency are they going to be? It's going to start that electron vibrating at the hydrogen alpha frequency, and when it falls, it's going to fall from here to here, which also causes it to emit hydrogen alpha. So there you go. Same phase, same polarity, but where's the mechanism to make them go the same direction? There might be something that I don't understand, but I think I do understand this. So that photon should be going out as a circle, in a circle of probabilities, and where's it going to interact? It could interact anywhere. So it looks like it, if you want to look at it as a particle, that it could go in a random direction. So we've got an incompatibility between the classical, here comes the photon, hits the electron, there go two photons. That's incompatible with how Fresnel reflections work. So I've been trying to figure out how to explain how a laser really works. And I ended up going down quite a rabbit hole and learning much more about the hydrogen atom than I ever wanted to. And I finally got to where the hydrogen atom was inadequate. It's a nice, simple atom to try to explain things with, but it doesn't have the right properties to do laser. And I certainly can't get into that explanation right now. And so if I wanted to really explain things, I was going to have to get into a molecule that could be used to make laser. And I thought, well, neon's used in helium neon lasers, and neon is the emitter. And oh boy, is neon complicated. As soon as you start adding more particles to the nucleus, these energy levels, even in the hydrogen atom, the energy levels have many sublevels, but you start adding more particles to the nucleus and adding more electrons, you get more and more sublevels, and it gets very complicated. And I thought, I'm going to have to become an expert in the energy levels in a neon atom. Now I thought, okay, I think we're done here. First of all, I don't have enough energy to do that. And I'm going to have to figure out how to explain it without going into all that information on neon. I think I have the explanation down, and you'll probably pick up on it here. But this has to be compatible with the modern conception of a photon being an expanding bubble of electromagnetic energy. So let's go back to our gain medium. You can see the direction I'm going here, and I'll draw it kind of big here. And I'll just draw a few electrons, and I'm not going to draw the whole thing full. And let's say somehow, like I said before, we can get all of these electrons to emit a photon at the same time. And let's say they're hydrogen atoms. Yeah, I know that won't work, but we're going to fudge it there. And so we get all of these to emit photons at the same time. So what's going to happen? They're going to start expanding and expanding. And let's see how we're doing here. I'm a little bigger than I wanted to get, but there we have our two wave fronts. One going that way and one going that way. Now that works. But what's going to happen? We're in a laser medium, which means that more than 50%, hopefully a lot more than 50% of these atoms are in a state where they're at a high energy level of hydrogen, even though we can't really make it work. Let's say in hydrogen, they're all at the n equals 3 level. So they're just waiting to interact with a photon and drop their electrons. So what's going to happen? This wave interacts with all of these atoms here, interacts with the electron in each of those hydrogen atoms. What's going to happen? It's going to absorb those photons, and they're gone. I hope I can make an illustration of this. So I'll just erase that there. So those photons are gone. So now these photons are going to each emit an electron. They're going to re-emit that energy they picked up, but they also stimulates them to drop down to a lower energy level and each emit another photon. So we're getting double the photons. I don't know how to draw that other than to just make it darker. So now we have double the photons. And of course those photons are expanding again, making that wave front, but now it's twice as strong, twice as many photons. So we have that wave front once again. When it comes to quantum physics, these wave fronts interacting as a concentration of probabilities. I'm not sure if that works in classical physics and anything, but in quantum physics, that's what we have. So our probabilities are concentrated here and here. They're going opposite directions. But when these interact with the next row of atoms, they're going to interact with those excited electrons, which are ready to drop their energy. And so those photons are all absorbed. I guess I could draw my atoms are still here. But these absorb all those photons, but then immediately re-emit them, and at the same time emitting new photons, so now they're 3 times as strong. So each time these photons go to another row of atoms with their electrons, it adds their photons to it, and so now it's three times as strong. And eventually we get to the same thing. Here are these excited atoms. Now here come all these photons. They're going to react, and now we get, these are all gone. And all the photons are now gone. And now we get, let's see, we had one photon made 2, 2 made 3, 3 made 4, 4 made 5. So now we have even more photons. Really a big gang of photons going down there. I think I miscounted. We had the first photons, then we had double the photons, 3 times the photons, now we're 4 times the photons. So the whole idea of a laser is we are getting some amplification of this light as it goes through the medium. And it's sort of a laser. In fact, you can make a laser with hydrogen that sort of works like this. And there are natural lasers, or at least masers. A maser is a microwave version of this rather than a light version out in space that sort of work like this, but they're not true because we don't have the next step, which is to put mirrors on the ends. So what's going to happen when this wave front, which is getting stronger and stronger, hits this mirror? Well, that mirror is, I don't understand this kind of reflection, so I can't explain it right now. I'll figure it out one of these days. It's going to somehow reflect all that energy back, and it's going to go back through. And now as it goes through this medium, which is all excited with all these electron's ready to drop their energy, it's going to do it again. We're going to have the same thing happen again as it goes through this way. Now we're going to put a mirror at this end, and that's going to go and hit that mirror and reflect back through, and we get all that light going back and forth between these mirrors, and just gets more and more amplified. And to make it useful, I suppose if we just had perfect mirrors here, but just you start building up heat, might damage it, might get to a point where there's an equilibrium because of how much heat is being dissipated and how much energy is being created or whatever, but it's not really very useful. So what we need to do is do something to get some of this light out, and there's two main ways they do it. One is to perhaps make this 100% reflective, at least that's what they say. It's not always that way. In fact, if you've ever seen a helium neon laser, you'll notice it has a beam going both directions, but that's neither here nor there. But let's say according to the classical explanation, one mirror is 100% reflective, and we'll say make this one 80% reflective. So that means that 1 out of 5 photons that hits this light here is going to go on out, and we now have a laser beam. Another one is to actually undo some of the silvering so that we get a few photons going through out with the part that's not reflective. And so we get a lot of light going back and forth in here. We're putting energy in either electrically or by light or whatever. We keep putting energy in, so we keep kicking those electrons up to high energy states so they're ready to drop their electrons. And we get this beam going through back and forth, and we eventually get a laser beam. All we have to do is find some way to get all of these to fire off at the same time. Or do we? Well, if we can get a whole bunch of these to fire at the same time anywhere, what's going to happen? So let's say like with a ruby laser where we have a flash tube. I'll just draw this is a cutaway. Let's say this is a ruby rod here. And so we flash that tube, and that energizes the atoms, and for a long enough time that we can get a pulse of laser, but we energize them all. Well, light's going to go everywhere because these are going to absorb the energy and then drop the energy, and light's going to go everywhere. But all the light that goes this way is going to be lost. All the light that goes that way is going to be lost. All the light that goes this way is going to miss the mirror and be lost. Only light that is right between these two perpendicular mirrors will actually be reflected back and forth through the cavity. So yeah, we lose a lot of light through the side, but we still get some light that's just by chance going to go perpendicular to that mirror. And so it's going to bounce back and forth, and we get that laser effect. So we don't have to energize one column of these electrons at the same time. We can just energize them all, and then only the light that just happens to be going perpendicular to these mirrors gets amplified, but being amplified it does. And so we don't even have to have all the atoms lined up in rows like I did. We could have a gas in there with the atoms moving all over the place, and we're still going to get a laser effect because of the fact that only the light that goes between the two mirrors is going to line up and go through that way. So even if the gas molecules don't line up, I'm not going to try to draw this, but if they're being made in sort of random areas, they're still going to develop that wave front and go back and forth between these mirrors, and we now have laser. So that's in a nutshell how I understand that laser actually works. And I don't know how well I've explained that. Like I say, I'm going to make another video and explain it better, try to do some animations. And I'm writing the explanation at the Vocademy website for the page on lasers. And I'm just about done with that, but that's what I've been doing for the last couple of weeks. So there you have it, my understanding of how laser actually works. So as opposed to the classical explanation of the particle coming through, reacting with an electron, and now two particles go in the same direction, we now have something that's compatible with the latest theories of how light actually acts, what photons actually are, what electrons actually are. So photons are these expanding bubbles of electromagnetic energy, and they will randomly react with an electron somewhere, and if it reacts with an electron over here, it disappears everywhere, but then that electron's going to make a new one eventually, and all kinds of things can happen. If you can think of it, it probably does happen. I've been doing a lot of research, and questions like, well, gee, if the electron can fall from this level to that level, or from that level to that level, or what's the probability? Which way is it going to fall? Well, they have a preference to falling one level, but they can fall 2 levels, or 3, or whatever. And so some will and some won't. So all kinds of things can happen So for example, in a tube full of excited hydrogen, you're going to get different colors of light out. You're going to get a red color that's hydrogen alpha and a blue color that's hydrogen beta, I think is the blue color, all at the same time, because some electrons are going to fall that far, some are going to fall 2 levels, some will fall even more levels, and there's several different colors of light that come from the different amounts of levels those electrons fall through when they give off their energy. There's other things that can happen too, like collisions that can send some of the energy of a photon into an electron and some of it goes somewhere else, and it can get pretty complicated. If you can think of it, it probably happens, and that's what I'm studying up on, and spent way too much time, learned a lot more than I ever thought I wanted to know, but there you have it, my understanding of how laser works really. Not the particle hitting it and 2 particles go away, which, why would they go the same direction? Now we have the expanding sphere model and the concentration of probabilities, which is compatible with at least my understanding of quantum physics. And so now we have these wave fronts going back and forth, not individual photons as the classical explanation, but wave fronts going back and forth. And only the wave fronts that are exactly between the mirrors are the ones that will keep getting amplified and eventually make the laser beam. Anything else escapes and is lost. There's a lot more to say about lasers. These mirrors might be curved. There's problems. For example, if you read about laser, they'll always call this a resonant cavity. Well, I've always had a problem with that, because one thing I know about resonant cavities, if that was true, the distance between those mirrors would have to be held very tightly to a multiple of 1/2 wavelength of the light being created. Well, if you have a helium neon laser tube about this big, thermal expansion is going to expand that multiple wavelengths. And I have not found a good explanation about how that's handled. I think that we end up with the particular material in the medium being more important than the distance between the mirrors. Apparently, in laboratory lasers, they can hold those mirrors very precise distances apart and use low expansion materials and temperature controls to keep everything very tight and have a very efficient laser. But then with a helium neon laser, where you don't have any of those temperature controls, not low expansion materials, you're going to get, I think a helium neon laser tube may expand 7 to 10 wavelengths of light, and it just reduces the efficiency. So they call it a resonant cavity, but it may be acting like a resonant cavity and maybe not. Maybe it depends on the laser. So that's just some of the things I'm learning, and still have some questions, but there's my understanding the best I can explain it at this point. So this is kind of an informal video, just telling you what I'm doing. I'll be getting back on track soon, I hope, and keep making videos that go with the class as I have presented it in the classroom, and also supplemental videos like this just to keep you informed of what's going on. So again, a big thank you for sticking with me, as I am the writer, producer, presenter, and editor of these videos and the website maintainer. I try to interact as much as I can, but I thank you a lot for continuing to support me, even though about all you get is something to read and an occasional video lecture, and I hope you find that useful. And if you do, please give me a thumbs up down below. It helps the channel, and subscribe and hit that gray bell so you get notified when I put up new videos. And of course, to help me monetarily, you can go to patreon.com/Vocademy and pledge your support, even $1 a month. Those $1 a month pledges add up and make a big difference. And of course, for one-time donations, you can go to paypal.me/voced, VOCED. So a big thank you to all of my supporters, and thanks to everyone for watching.